All right, babies, welcome to section 10.4. Today we're going to talk about perpendicular lines, which we introduced to you guys in section 1. And now we're actually going to get into the idea of perpendicular lines and some special theorems behind them. So again, as a quick review, you guys should already have this definition, but perpendicular lines, again, are going to be two lines that intersect. And what's different than what we've been talking about, we've been focusing on parallel lines and angles formed. We looked at those transversals that intersect, but specifically, perpendicular lines are going to be where they intersect at 90 degrees. So again, a 90 degrees is going to be our right angle, and what you're going to see for perpendicular lines is at the intersection point between them, you're going to have one and all four of those angles are going to be 90 degrees. Okay, so what we're going to do today is we're going to look at some special theorems that go along with perpendicular lines, and also going to apply some knowledge of some of the things we talked about with parallel lines as well. All right, so some of the special theorems with perpendicular lines. First one, we're going to talk about the linear pair for perpendicular lines. So this one's just kind of just a happening of when you have two lines that are perpendicular. And what this says is that anytime you have two lines that are perpendicular, essentially, this is when any lines intersect, but specifically when two lines that are perpendicular intersect with each other, that they essentially form what's called a linear pair. And a linear pair, again, is an angle relationship for two lines that, or two angles that form a line. So for example, you have here angle 1 and angle 2. Angle 1 and angle 2 would be considered a linear pair. So what this says is that if these two angles are congruent, then we know that these two lines are perpendicular. And here's the idea. Anytime you have a linear pair, what that means is that the two angles add together to give you 180 degrees, because the angle measure of a straight line is 180 degrees. Now again, what this theorem states is that if the two angles are congruent, then these lines are perpendicular. So the idea of them being congruent is that angle 1 and angle 2 are equal to each other. So the measure of angle 1 here would equal the measure of angle 2. So by just using this, we can actually figure out what angle 1 and angle 2 have to equal, because if they're both the same and they add up to 180, that means the angle measure for both of them would be just simply 180 degrees divided by 2, cut in half. So 180 degrees divided by 2 or cut in half would be 90 degrees for both angles. So angle 1 and angle 2 would both be 90 degrees. And what does that mean then is that if they are 90 degrees, that these two lines are intersecting at 90 degrees, which means that they are perpendicular, okay? So if we ever see that those two angles are both 90 degrees, we automatically know right away that those two angles are perpendicular, and that's technically what it means for lines to be perpendicular. All right, our next theorem is going to look specifically at what we talked about last section. We looked at the idea of parallel lines and transversals and the angles they form. So we talked about all the different special types of angle relationships, right? We have like our corresponding angles, our consecutive, or what I call same side interior angles, your alternate interior angles, your alternate exterior angles. I can go on. Now, what this says is that if we look at those same types of problems we did in our last section, if the transversal is perpendicular to one of these lines, so in this case here it's showing that line J is perpendicular to line H. Perpendicular means that, again, they're going to intersect at 90 degrees. What this theorem says is that if a transversal is perpendicular to one of two parallel lines, then it has to be perpendicular to the other. So that means if it's perpendicular to H, it's got to be perpendicular to K. All right, this last theorem is going to be saying the same thing we just talked about in the previous one, but this is lines perpendicular to a transversal. Essentially, it's saying that if we have two lines that are both perpendicular to the same transversal, the same line. So here it's showing that line M is perpendicular to P. Line N is also perpendicular to P. What it says then is that those two lines have to be parallel. So M and N are going to have to be parallel to each other. So what we can do is we can take these three theorems and we can apply them to prove that things are parallel or perpendicular. We can also use them to find angle measures. So in our first example here, what we're going to do is we're going to use this idea of perpendicular lines to try and find angle measures. So here we have a whole bunch of lines shown here. What I want you to recognize is this is going to utilize some of the relationships we talked about. What I want you to recognize is that I have my line going up and down here. I'll highlight this line. So I have the line, my vertical line here, and I have my horizontal line here. And what I want you to notice is the angle that's shown right here. So what that's showing, that little box again, is showing that this angle is 90 degrees. So our goal is using that one angle. We have to find all the other ones. And we want to find angle 2, 3, 4, and 5. So this is going to utilize some angle relationships that we should already know, as well as some of the things we just talked about. So first of all, if we know that angle 1 is 90 degrees, I want you to recognize across from angle 5, that angle 5 would be a vertical angle, okay? Let me just write that down for you. So angle 5 is a vertical angle, and hopefully you remember that vertical angles are always going to be congruent to each other. So that means that angle 5 also has to be 90 degrees, okay? So that means at this intersection point that angle 1 and angle 5 across from each other have to be the same. They're both going to be 90 degrees. So how do we use then this idea to solve for 2, 3, and 4? Well, what we also know is that at a perpendicular, or at the intersection of two perpendicular lines, if one of the angles is 90 degrees, essentially it forms a linear pair. That this angle plus the big angle here, and I'll label this here kind of with this little loop, that this would also have to be 90 degrees. They form a linear pair. So if this chunk right here is 30 degrees, our goal is to find the chunk next to it labeled angle 2. So how do I find that? Well, I know that angle 2, and I'll write this down algebraically, the measure of angle 2 plus 30 degrees should equal the total of 90 degrees. So therefore, I can solve for angle 2 by just subtracting 30 from both sides. And that would tell me then that the measure of angle 2 is 60 degrees. So I now found the measure of angle 2. And again, that's looking at that by being a linear pair. All right, so that leaves us with angle 3 and 4. So angle 3 and 4, what I want you to notice, again, the idea of a linear pair like I just solved, that angle 5, which is next to it, and these three angles, 3, 40 degrees, and 4, that these three angles are going to form a linear pair, which means that those three angles are going to add up to 90 degrees. So the measure of angle 3 plus the measure of angle 4 plus 40 degrees, all of those should add up to 90 degrees. So that means I'm missing two angles here. Now the tricky part is that how do I figure out what those two angles are going to add up to? Well, by taking away, starting off, if I were to take away 40 degrees, I know that what I have left, my two angles, the measure of angle 3 plus the measure of angle 4, well, I know that those should add up to 50 degrees, because 90 minus 40 would be 50. So then how do I find the measure of angle 3 and angle 4? If you look at the angles, and normally we don't like to just look at a diagram and try and tell things, but I can see that angle 3 is a little bit bigger than angle 4. So I cannot say that each of these are 25 degrees apiece. So I'm going to have to figure out what they are. So using the diagram, this is again going to use the idea of vertical pairs. So what I want you to recognize is that I have angle 3 and angle 4. Now angle 4 is not really a vertical pair with anything, but if I notice angle 3 is a vertical pair with angle 30. These two are vertical pairs because they are formed by two intersecting lines. This intersecting line here and that intersecting line there, which means that 3 is vertical to 30 degrees. So based on that, I know that angle 3 also has to be 30 degrees. So that means angle 4 has to sum with 30 degrees to give me 50. And based on that, I know then that the measure of angle 4 has to be 20 degrees. So based on this, I've now figured out what all the angles are. I know that angle 3 is 30 degrees. Jot that down there. I know that angle 4 is 20 degrees. If I were to add up 30 plus 40 plus 20, 30 and 40 give me 70, 20 would give me 90. And again, I know angle 1 was 90, and I know angle 2 is 60 degrees. So a lot of meat and potatoes, but we can use all these angle relationships to find unknown angles. All right, now this is a fun one. Here we have our parallel lines, H and K. And this is a similar diagram we had before. So our goal is to find the missing angles. So here's H, here's K. Based on those arrows, we know that those two lines are parallel. J cutting across those two parallel lines is known as my transversal. And notice up here, you are given the box, which means that angle 2 is 90 degrees. And our goal is to figure out what are the missing angles 1 all the way through 8? So we dealt with similar examples last section. So here what we got to do is use some of our angle relationships. So for example, I can say angle 2 and angle 6. Whoopsies, that's not a 6. There we go. These are going to be corresponding angles. They're in the same location. And if we remember, corresponding angles are congruent. So if I know angle 2 is 90 degrees, then I know angle 6 is 90 degrees. Okay? I can say, ooh, angle 2 and angle 7. They're alternate exterior angles. What? Get out of town. And I know that those are also congruent. So I know that angle 7 has to be 90 degrees. Okay, well, let's see then. Let's say that angle 7 and let's say angle 3. Angle 7 and angle 3 are also corresponding angles. Get out of town, babes. When we said corresponding angles are also congruent, so I can say angle 3 is also 90 degrees. Gosh, I'll tell you, folks, this is just exciting. So hopefully you can start to realize here that, yeah, 2, 3, 6, and 7 are all 90 degrees. So based on this, we can talk about that all the angles in this diagram are going to be 90 degrees. And this goes into one of the theorems that if I have a transversal that is perpendicular to one of 2 parallel lines, that means it also has to be perpendicular to the other line that is also parallel. So that means if J is perpendicular to H, because H and K are parallel, that means J is also perpendicular to K. All right, babes, in these next examples, we're going to try and figure out which of the lines are parallel. So we're going to utilize some of the theorems we talked about at the beginning. So in this first problem, we just want to identify, we have lines A, B, C, D, and E. Which ones are parallel? So again, parallel lines, as we should know, parallel lines do not intersect with each other. So any lines essentially that do intersect, we know that are not parallel. So I know, for example, that B and E are not parallel to each other. I know that B and C, B and D, they're not parallel to each other. I know A to C, A to D, and so on and so on. So I want to identify the ones that are parallel. So parallel lines, again, don't intersect. So based on the diagram, we have a couple options. First of all, A and E, I don't see those lines intersecting. However, if you continue again, we talked about this. Here's line A, here's line E. Even though they don't intersect now, those 2 lines will eventually intersect, meaning that A and E are not going to be not going to be parallel because they will eventually intersect with each other. I can look at C and D. They also kind of look parallel. But again, based on the angles, I cannot say with certainty that they're parallel. It kind of looks to me like C's got a little bit downward lean to it, which means eventually it would intersect with D. But what I do want to recognize is A and B. Notice that A and B, by the diagram, you can see that A is perpendicular to line D, and B is perpendicular to line D as L. So, since these 2 lines, A and B, are both perpendicular to D, that means that line A has to be parallel to line B. Oh, I wrote a fancy L and then I wrote a regular L. That's interesting. But I know that line A and B are parallel because they are both perpendicular to the same transversal D. So again, when you have one line that's perpendicular, 2 lines that are perpendicular to the same line, then that means that A and B in this case are going to be parallel. In our next example, we're going to do the same thing. We have lines A, B, C, and D. It's kind of a sky view of a city with the streets. Again, I want you to recognize within this diagram that line A and C are perpendicular to each other based on that. I can see that A and D are perpendicular, and I can see that B and D are perpendicular to each other. So first of all, what I should be able to recognize is that since A and B are both perpendicular to D, that means right away I can tell, okay, that A has to be parallel to B. So I know that A is going to be parallel to B because they are both perpendicular to the same line. Now, what about C and D? Are C and D going to be parallel? They kind of look parallel, so how do I prove it? Well, notice that when I see over here, we have this angle we already looked at. Notice that line D is perpendicular to A. Well, if I recognize up here, line C is perpendicular to A. So since line D and line C are both perpendicular to A, well, that means that line C and line D also have to be parallel to each other. So I know that A is parallel to B because they're both perpendicular to D, and I know that C is parallel to D because they're both perpendicular to A. So again, this is using that when two lines are perpendicular to the same line, that means that they are parallel to each other. Fun stuff. All right, last type of example here is, let's say that I want to find the distance from a point to a line, especially for a point that is not on that line. So this is an application of perpendicular lines that if I have, let's say, line M here, random line, and a point P that's not on M, and I want to find the shortest distance. That means if I were to draw a segment, let's say, for example, from P to this line, and I want to draw, let's say I draw a segment that looks like this, a segment that looks like this, and let's say that I were to measure these lengths, how would I find the shortest length? So the idea is that the shortest length is going to be the line that is perpendicular to that line M. So if I were to draw a line, in this case just straight down from P, such that it's perpendicular to line M, which means it forms a 90-degree angle, that this length right here is going to be the shortest distance. So the shortest distance from a point to a line is always going to be the distance that is perpendicular to that line, called that perpendicular distance. Okay, so last and final example, we're going to use that idea that the shortest distance between a point and a line is going to be that perpendicular distance. So I want to know what is the distance from point A to BD. So point A right here, BD is the line that's down here from B to D, and I want to find the distance. So we're going to use the shortest distance. So notice with my point and with the line, we're going to try and find the perpendicular distance. So recognize my perpendicular line is going to be the line that connects A to our third point on the other line, C. So if I want to find that shortest distance, essentially what we're going to do is we're going to find the length of AC. Okay? So we are given the 2 points. We know that A has the coordinates of -3, 3. We have C that has the coordinates of 1, -1. So if I want to find the length of that perpendicular distance, we're going to need to use the distance formula. And the distance formula is what you guys should have learned way back in Chapter 8. Distance formula is going to look at the difference between two of the x values, so x2 minus x1 squared. It's going to add that to the difference between the two y values squared. And if I take the square root of both those things, that is going to find the overall distance. So looking at my x values again for A, think of this as x1 and y1. Think of this as x2 and y2. So to find the distance, all I'm going to do is plug those x1, y1, x2, y2 into my distance formula. So starting with, I have the square root, starting with my x's, x2, that is by c, so that would be 1 minus x1, which is -3. Whatever the difference is there, I'm going to square that. And then plus, we're going to do the difference between the y values, so y2 would be -1 from point C, minus the y1 from A, which is 3. And again, whatever the difference is, we're going to square it. And then after that, we're going to add those two squares together and square root. A lot of meat and potatoes again. Kind of running out of real estate here. Whoopsie daisies. So we'll start off and solve what's in parentheses first. So 1 minus -3, that's going to give me 4 squared, one of my favorite games. And then we have -1 minus 3, which would give me -4 squared. And I'll put parentheses around the 4 as well. And then again, I got the big square root symbol around it. So that's going to give me the square root. 4 squared is 16, plus -4 squared. Again, the -4 is in parentheses. That's also going to give me 16. So I have the square root of 16 plus 16, which would give me the square root of 32. So plugging that into your calculator, you are going to get an exact answer of 4 radical 2. And if we were to round that, we would get a decimal about 5.66. And again, that's rounding to the hundredth, so 5.66. Either answer is fine. Just be careful in big ideas if it's asking you for the exact answer or the decimal answer or where to round. But again, we found the shortest distance between that point and that line by looking at the perpendicular distance and then relating back to what we learned in Chapter 8 using the distance formula. All right, so in this section, we just applied some special concepts of perpendicular lines. Notice it did combine some of the ideas you learned about in our first two sections on parallel lines. But again, it's just that idea of perpendicular lines being 90 degrees and how we can apply those things. So you got any questions, make sure you write those things down. Otherwise, we'll see you at the next video lesson. Peace out.